Hello, ladies and gentlemen. This is Mr. Hunter, and this is your Wave Notes Part 2. Last time we were talking about the basic characteristics of waves, which includes what a wave actually is, its wavelength, frequency, period, amplitude, the parts of a wave that make it a wave. And then we talked about two types of wave, which is the longitudinal, which means that basically the wave or the matter moves parallel to the energy, and transverse, where the wave or the matter moves perpendicular to the energy. What I want to do now is kind of get into a little more specifics of waves. Talk a little bit about wave interference, which you'll record on the next capture sheet, and talk about now get into more specific aspects of waves. Last time I didn't get to talk about it, but it was the standing wave. When talking about a standing wave, one thing that we have to mention is we actually have to mention interference. And interference is when you send two waves or pulses of energy towards each other. They can do something they called interfere. And interference is when the waves add up or subtract when they overlap. I should have given you the capture sheet for this because there's so much information that there's multiple capture sheets. So we have two types of interference. We have constructive interference and destructive interference. Now, constructive interference, as I talked about in class, is when the waves add up. So that's, remember, amplitudes can be positive and negative, aka on the top of the line or on the bottom of the line. And where they're both on the same side of the line, they can add up. Why? Because 1 plus 1 is 2, and -1 plus -1 is -2. So it essentially will add their amplitude up, making a bigger wave. Or they can destructively interfere. That means the wave amplitudes can subtract. So if I have a +1 and a -1, they're going to subtract to 0. So how does this equate to sound? Well, sound, if you have constructive interference, the sound gets louder. In the same case, light gets brighter. Just remember, as review, amplitude equates to the energy. Why? Because if I'm getting louder, that means I'm putting more energy into my voice to speak louder. For light, like I'm making more electrons flow through the light to make it brighter. So therefore, it's more energy. So amplitude equates to energy. Now, with destructive interference, the sound gets softer or quieter with destructive interference, and that's like your noise-canceling headphones. What they actually do is they take the input waveform that's coming in from the noise, that wave, and they actually send out the counter wave. So they send out the opposite amplitude so they can cancel out that wave. And in the same way, light gets dimmer. Just real briefly, because it's really simple, a reflected sound wave is an echo, as you know. But the reason why I want to say all that is because now we're at something called a standing wave. A standing wave is waves of the same frequency interfering, or they interfere with each other. And since they're the same frequency, when they interfere, it actually makes it look like the wave is kind of quote unquote standing still. And so you can actually see the waveform, because most of the time when you send the energy down, you really just see the wave moving. You don't see necessarily the wave itself. So the points on that wave that the wave is like kind of not moving, that is called a node, and that's a destructive interference. So for example, if I draw a waveform right here, so like I'm just going to draw a mini waveform, and we're going to pretend this is a standing wave. The node, or actually I'll draw another wave. So here's two waves that are basically interfering. And so the nodes are the point where they perfectly cancel out. So that's called the destructive interference. That is the node. The antinode is constructive interference. So that's the antinode, and that's where they add up. Now, if you always notice, if you count the nodes, there are 5 nodes, and there are 4 antinodes. And there will always be one less antinode than there are nodes, always. That's just the case. And if you notice, one whole wavelength, so if I were to trace over this, one whole wavelength consists of 3 nodes and 2 antinodes. So that is standing waves in a nutshell. and it's just waves of the same frequency interfering, which creates nodes and antinodes. So now I want to get into, let's talk about sound first before we talk about resonance, and I am in the wrong file. Before we talk about resonance and the Doppler effect, let's talk about sound. So in class, we've talked about sound a lot already, so this will be review, or should sound like review, which is good because you need to hear things multiple times. As stated in this class, this unit is mostly conceptual, so you really need to know this information by heart because there's less math. So a sound wave is longitudinal, it's a compression wave. And as I'm speaking, my vocal cords are vibrating, and that vibrates the air molecules in front of my mouth, which vibrates the air molecules in front of that until they reach your ear. So it's a compression wave, and it's longitudinal, which means that the energy is traveling parallel to the air molecules. So it's vibrations, so you need matter to travel. So that makes it a mechanical wave. Remember, a mechanical wave is where you need matter in order for it to travel through. So sound travels the slowest in gases, then liquids, and the fastest through solids, because if you think about it, like the pictures I've drawn here, the molecules are all spread out in air. So it takes a little more time to push those air molecules in front of it. In liquid, they're a little closer, and in a solid, they're really, really close, so sound travels fastest through solids. Remember, frequency means pitch, so a higher frequency means high pitch, low frequency means low pitch. So this is a low pitch sound, and I'm not going to repeat the high pitch sound, just pretend it's a gingerbread man from Shrek. So once again, amplitude is loudness, and then one thing that we talked about in class is, and read about in class, is an increase in temperature actually increases the velocity for speed. Speaking of speed of a wave, one thing that I forgot to mention is that, oh, I was right in that file. Anyways, so one thing I forgot to mention is the only thing that changes speed is the medium. So V is constant unless you change the material you are traveling through. So we know the equation V equals lambda F, lambda being the wavelength, which is in meters, and frequency being in hertz, which is 1/2, which gives us meters per second. Velocity equals lambda F. And the velocity is constant if your medium stays the same. So when I'm talking to you through these airwaves, it's moving at 331 meters per second. But if I were to, yell underwater and you put your ear in water and listen, it's actually moving a little faster. So velocity only changes if the medium changes, which means that these two variables actually are the ones that change because velocity is constant. So if I change my frequency, I change my wavelength, or if I change my wavelength, I change my frequency because the speed is constant. So that was sound in a nutshell. Now we have something called the Doppler effect. So you might have heard this term before, and basically in the Doppler effect, let me just get down to the definition. Sounds that are moving towards you have a higher pitch or an apparent pitch that are higher in frequency. Think about an ambulance. When an ambulance is heading towards you, it's only letting out 2 tones. But as it travels towards you, you hear a higher pitch. And the reason why is because the waves are bunching together, which means, think about it, shorter wavelength, higher frequency, as we just talked about, because the speed stays the same. Since speed stays the same of that sound wave, they're kind of going towards you, and so the sound waves are bunching up, which means it gives me a shorter wavelength and a higher frequency, and I'll show you a picture of that in a second. And behind it, and now as that ambulance passes by you, the sounds that are moving away from you have a lower pitch because the waves spread out because you have a lower frequency and longer wavelength. So check this car out. And yes, I do want you to write this stuff down in your notes. As the car is just standing there, like just holding down on the horn, it emits a sound wave, a spherical sound wave around it. Why? Because sound travels out in all directions. So as it's moving towards you, the sound waves are always at a constant speed. However, you are moving the car. So those sound waves that are let out in front of the car kind of close in on each other. And so here we have a higher frequency and we have a lower wavelength because the wavelength is like the area between these waves. And here, and so that is higher pitch. Whereas in, let's say now it passes you. Well, as it passes you, the frequency goes lower and the wavelength increases. So we have a higher wavelength, but a lower frequency because those waves are now spread out more. And so that's why when an ambulance or a car that's laying on its horn, when it's coming towards you, it seems like a higher pitch, and moving away, it's a lower frequency because of what's called the Doppler effect. And light does the same thing. So I have an example of a sun, and this is how we know our universe is expanding. Because when we look at light from distant stars, we see a redshift, which means it's getting further and further away from us because the wavelength is spread out. Whereas if something's moving towards us, we see an actual blue shift in the light, which because it's a shorter wavelength, higher frequency. So the last thing I wanted to talk about real quick, because I am out of time, is resonance. Resonance is when energy is shared between objects of the same frequency. So in this case, I have these 3 cups filled with water, and the tuning fork is at 256 hertz. Well, as I strike the tuning fork and hold it above the different bottles of water, as we'll do in class or have done in class, one of them kind of hums. Because what ends up happening is that bottle, or those air molecules, take the energy from the tuning fork and they start to actually vibrate. And this is real. This is why opera singers can break glass with their voice, because it's a really high pitch, and so they're at the natural frequency of the glass, which makes it vibrate because it starts sharing the energy, and it breaks because it's a solid structure, but you vibrate the molecules, which makes it break. So I will see these in class to check your homework. Have a good one.